Right.
Yeah, I guess I still haven't worked out how to get sound on through the HDMI cable. Presumably if it doesn't work for me, it doesn't work for anyone, but I haven't called the IT people to, I think there's a problem with here. So anyway, so I guess I can narrate these just as well as anything else. As the narrative for this is, he says something about tornadoes in Ontario in 2017, and so this is a wind tunnel. I think at University of Western Ontario, which is in London, Ontario, just a couple of hours out of Toronto, I think. And so what they're doing is they have a mock-up of individual buildings that have roofs on them, and they're attached to some degree, not fully, and then they're running air through it to look at what wind speeds you need to get before you get uplift and you start destroying these individual buildings. And so it's not an unusual thing to do in design, is to use scaled models to be able to figure out how things behave, not only for things like you'd imagine being in wind tunnels, like scaled airplanes and whatever, but also for buildings. And one of the things is that the flow around the building relies on the other buildings around it. So if you're building the new super slim skyscrapers in New York City, which are only probably, I don't know, 60 feet by 60 feet, a fraction of a block in plan, but go up higher than all the other existing buildings, then sometimes you need to know what the wind loads are on those, and you need to take into account the buildings that are around those. So this actually is quite a famous wind tunnel. It's there's a guy who's now dead called Alan Davenport, who was a pioneer in this particular area, and he used to work at University of Western Ontario. And there's a company now named for him, and I think that this still continues as a specialty for their group. And so other things as well. You can imagine if you're interested in finding out what concentrations would be from a stack that are downstream, and there has some. I'm not sure that the buildings here would make much difference in terms of what the distribution would be, but if you want to be able to figure out exactly what that is and how it changes, perhaps with wind speed, what the concentrations you'd get, you could certainly do pattern recognition on the dyed smoke and be able to figure out what concentrations are, or of course you could sample what concentrations would be from individual components. What else we got here? Something you could probably relate to as well. And again, a scaled model of a bridge. I guess this is going to run a bit longer. It's not super clear on my screen. Oh, that's a bit better. And so probably in your high school physics classes you've seen the Tacoma Narrows Bridge. This is not it, of course, but the problem is the same, and that is that if you get wind blowing over at some speed, then you can get vibrations resulting from it, just like plucking a guitar string. It's really quite similar process. And so that's why I guess armies or troops walking across bridges are told to break step, not to march in step, so that you don't have a resonant frequency applied to the bridge. And in this case, it's applied by the wind. And so for Tacoma Narrows, it's not so much that it's a high wind, but it's a constant wind at a particular frequency. And just like a guitar string that has a resonant frequency, that's the sound you hear, a structure would also have resonant frequencies, a major one and minor ones, at which if you supply an excitation at that particular frequency, then you put it into resonance. And so the mechanism by which it works, I think we might have talked about it when we started off in the class, is that when wind gets shed on the other side of the girder, it'll alternately create a vortex off the top and then shed one off the bottom in sequence and keep on doing that, top, bottom, and that vortex gives a little jolt to the bridge, and it is in some kind of frequency that's related to the wind speed. And so if the wind speed happens to be the wrong frequency, or just the right frequency for that resonant, if the excitation from the wind because of the geometry of the bridge, gives the right impulse that's identical to the resonant frequency of the bridge, then that's a problem. And so to solve it, you can change the resonant frequency of the bridge, and to do that, just like a guitar string, you tune it so it's not quite so taut, and it will change its frequency. For a bridge, I guess you would put on some damping weights or try and do some damping that would stop it from moving at that frequency. And I guess we haven't learned too much from that. This is the Millennium Bridge. I guess it was built in London in 20 years ago, I guess around the time of your birth on average, right? And I guess this has closed captions on it, but you'll see. So it's not completely, it's getting there. And so the problem with the Millennium Bridge, it's a bridge across the Thames in London, a walking bridge only, and this might have been its inaugural day, perhaps. I'm not sure why there's so many people here, but you can see, I think that's not, that's a true motion. So they built it, it had this motion in it that had this resonant frequency. I think this isn't the wind, but it's the people perhaps in this case, I'm not really sure. But you can see that it's a frequency that probably doesn't make people feel super well. You can see there's those vertical stanchions up at the back moving all over the place. And so it's solved, I'm sure they added some damping to it or some weights to it that changed the resonant frequency of it, and you can solve it by retrofitting in that way. And so that's kind of something that we will begin talking about now, I suppose. Well, not exactly today. So we got through with the test. You got the email from me on, I guess yesterday morning, very early yesterday morning. So the trajectory of the scores, I think it's going in the right direction. It's quite normal. The scores are in line with what they've been in the past. And so if people want to talk to me about their scores, I mean, I can't do much except to say that you're kind of in control of your own destiny, and the only thing that is a truism seems to be that scores with the tests as we go through the semester go up with each individual test. I'm not sure if that's because people are more used to taking them, or people are more engaged, or the tests are getting slightly easier, or they're more formulaic. Certainly in the ones that will come up this week or last week, week 9, would have been dimensional analysis. There's always a dimensional analysis question on the test, and it's very formulaic. You just got to put the numbers in the right place, and you can always guess exactly what would come out of it, and you can check your results quite readily as well. So I think when we start talking about what we'll talk about in the final part of this class, so last week would have been dimensional analysis. So dimensional analysis is the method that you'd use to analyze some of the experiments that we just looked at in the wind tunnel. You can figure out what the non-dimensional parameters would be that would govern behavior. When you look at the material for last week, if you haven't already, you'll find out that there are two important parameters. One is the Reynolds number, which we'll talk about, which defines the geometry of the flow, whether it's laminar or turbulent. And the other one is the Euler number, which defines the pressures on the structure. So if you want to see if a skyscraper is going to get blown over, you want to know the pressure on the windward side versus the lee side, because that's a force that's applied. If you want to know whether a plane will get off the ground, you'd like to usefully use forces of lift to be able to lift a wing. And so then the two numbers that are important are the Reynolds number, which defines how the flow field looks around the wing, and the second one is the Euler number, which defines how much force you'd have on the wing as a function of the wind speed, or the speed of the airfoil. So dimensional analysis is an important thing that we'll use, and we'll use that to apply to three topics really. And the three topics are flow in pipes, which will be this week and next week. It will be flow around external flows on structures, which would be flows on an airfoil or a wind turbine blade, for instance, how you transmit flow from the fluid onto the structure. And then finally, flow in open channels, which is like pipe flow, but the pipe is only half full. And so you don't have pressure driving the flow, you just have gravity driving the flow. So those are the things that we will look at in these final portion of the class. So I guess I'll just go on this. So I was going to kind of summarize where we've been, because it's probably useful in looking at that. And I have this, I guess I wrote this out last year, so I still had it. So I won't rewrite it again, but it's just to put everything in context for where we are. And so we started off with the idea that we can use Bernoulli. And Bernoulli allows us to be able to look at flows from upstream to downstream. It's really just a reformulation of Newton's second law, which allows us to account for the fact that fluids, when they're accelerated, they have a resistance to acceleration, which is due to inertia. And when you stop them accelerating, for instance, you can apply forces onto structures like the truck being pulled behind the 747 engine, or whatever plane it was. So at stagnation, you get a force applied as a result of that. And it's really written in one-dimensional form, as we've had it in terms of these upstream and downstream equations. The initial Bernoulli was just these red terms, of course. And that is for the case when it's inviscid, when the viscosity is equal to 0. And that means that there's no friction losses in the system, and we can use just these red terms between upstream and downstream. Doesn't matter which ones are upstream and downstream, but they have to be equal to each other. If we only have 4 terms, and we need to get 2, then we can also use the idea of conservation of mass. Conservation of mass in our simplest term is mass rate in equals mass rate out for the stream tube, and so we can close the system of equations with this if we need to. Densities typically remain constant in the cases we're looking at, so it's just area times velocity upstream and downstream. We found out, though, that instead of writing it just for a stream tube, we could also write conservation of mass in a more sophisticated way, where this term on the left-hand side, mass rates, the sum of mass rates into a random shaped control volume, we could sum them, and they had to sum to 0 if there wasn't some accumulation. And that accumulation could occur because of 2 things. Either the density could change, like filling up a tire with the air. Obviously the volume of the tire isn't really changing very much, but the density of the air is changing as you put more air in it and the pressure builds. Or the volume can change. And so the volume would be, if you're filling up a bucket, that the area included under the free surface as it goes up extends. So these are the mechanisms of accumulation. So Reynolds transport theorem was a formalism, if you like, for us to be able to do that. If we wanted to be more sophisticated in when we write Bernoulli for conservation of momentum, and so this definitely, the red terms here are for conservation of momentum because it just satisfies Newton's second law, then we can do that. I guess conservation of momentum, what was it? It's sum of forces is equal to the sum of velocities times density times velocities, v squared, right? And so if we want to be able to write Bernoulli in a more sophisticated way, we can write it in this form here, and so that we end up being able to be solved for more complex bodies. And so that's fine. So we have both conservation of mass and conservation of momentum. And those are really the analogs of the red portions of this equation here and this equation, so these 2 equations. But what it doesn't allow for is the case when the viscosity is not equal to 0. And so that's the essence of all practical problems that we would deal with typically. You can solve a lot of problems using Bernoulli, but many problems involving, for instance, flow in pipes, where the essence of the problem is that you're losing energy as you flow from upstream to downstream, is that you have to be able to account for these frictional losses. And the mere, I guess the observation that you do have frictional losses is that if you measure pressures between upstream and downstream, so if you measure a pressure differential So if you apply pressure upstream and you have a length of the pipe as you're flowing water through it, the fact that you're losing pressure as you're going from upstream to downstream, if you put that into Bernoulli, you'd find that if it's the same elevation, the elevations wouldn't change. If it's the same cross-sectional area, then by definition, these two terms wouldn't change. And therefore, if you have the pressure upstream and downstream should be the same if there's no viscous losses. In reality, for pipe flow, there's a drop in pressure as you go from upstream, and so we need to be able to accommodate that somehow. And so conservation of energy allows us to do that. We ended up getting some expressions for conservation of energy, both from a kind of a phase change behavior, but the more usual one that we'll use is the one that incorporates the one-dimensional flow just into a Bernoulli-like equation. And we can do that by applying two components. One is that we can put energy into the system as a pump head, and we can have energy losses in the system as a head loss. We write it between upstream and downstream. It always has to be upstream to downstream. The convention is that head losses are always positive. You always lose energy. I've done it with pulling my backpack across the counter. And the convention for pump heads is that if it's a pump, if you're putting energy into the system, it's positive. And if you're taking energy out of the system, such as a turbine, then this term would be a negative value would come out. And so the easiest way to think of this term is in terms of this grade diagram with the energy grade line, is that you have flow. It's a horrible diagram up here, but if you have flow, let me replace it with something that's a bit better. If you have flow from upstream to downstream, this would be V2, this would be V1. You have a pump in there with a pump head, and maybe I can get rid of this horrible figure here, don't like it. Just replacing it. And you can think of this in terms of the Bernoulli relationships. Why did it do that? And that is that relative to some datum, we have an elevation head, we have a pressure head, and we have a velocity head that add together to give us the behavior upstream. If it's a constant diameter pipe, then and it's horizontal, then these have to be replicated on the right side. But we also have individual terms in addition to that, in that we have potentially a pump head that's added, and we have a head loss which is subtracted. In this case, they would balance each other exactly, and the energy grade line, instead of being horizontal, has a drop in it that says that as you go from upstream to downstream, you're expending energy. That energy is basically taken up by having frictional losses on the inside of this cylinder, and that they're being eaten up by that. And so the individual components of that, I guess when we talk about pipes, we'll find out that these head losses, we've seen them already in some form. They can be this, we've called it the Darcy-Weisbach loss term for bends in pipes. But we can also define this loss for pipes in terms of a friction factor, a length of the pipe, the diameter of the pipe, and also V squared over 2G. And so the velocity has to be the velocity in the pipe. In terms of this pipe here, we'll do this in a fair bit of detail. Then this would be the length, and this would be the diameter, obviously. And so it's relatively straightforward for us to be able to do that. So this is kind of catching up from where we are. So this is the essence. So the expression that we'll use both for internal flows and external flows, internal flows being pipe, external flows being a turbine blade, say, will be the same. It'll be Bernoulli's equation. And accounting for the fact that viscosity is real allows us to be able to deal with it by just including head losses in the system. And of course, this allows us to be able to calculate, by balancing this, what the energy we can get out of some system would be, like running water through a hydropower dam. So that's kind of where we're going with this. Last week, obviously, we didn't meet in class. You might have reviewed the stuff from week 9 already. But just to, in a nutshell, if you like, what that material talks about, it's relevant to the videos that we just saw. And that is that in week 9, the topic was dimensional analysis or similitude. And the idea is that relative to those videos we looked at where you use a wind tunnel as one format of the experiments that you might run, you can do a minimum number of experiments and cover all the parameter space with a minimum number of experiments if you follow a relatively straightforward procedure. And that is called, if you've looked at it, it's called Buckingham Pi theorem. It allows you to define exactly what the non-dimensional parameters would be. And it requires that you satisfy 3 conditions. You satisfy geometric similitude, kinematic similitude, and dynamic similitude. And geometric similitude is that the model that you have is a scale model in every aspect. So if you shrink down a plane to fit in a wind tunnel, then you shrink down every dimension so that the wing length in the prototype is scaled in the same dimension, same ratio to the wing length in the model. And the fuselage diameter also is scaled in exactly the same ways. So that any characteristic dimension in the model is equal to the ratios of those characteristic dimensions in the true life prototype. And so that just means you shrink everything down. So you'd expect that this is what you do anyway. The second one is that you want to have kinematic similitude. Kinematic similitude means that the flow regime around your model, or in your model, if it's flowing in a pipe, of course a pipe, having flow in a pipe and measuring the pressure upstream and downstream would be its own model, right, in some respects, that you can do an experiment on. And so kinematic similitude means that the Reynolds number in the model and the Reynolds number in the prototype are exactly the same. And so Reynolds number, we haven't dealt with it yet, but we talked about it in the first week. It's really like many dimensionless numbers, it's just a ratio of forces. It's a ratio of the inertial forces to the viscous forces, inertial losses to viscous losses. And the essence of the inertial forces is F equals ma, that's inertia, right? Ma is the inertia. So it's related to the density and its velocity and some characteristic dimension. Characteristic dimension would be the diameter of pipe or the diameter of a sphere for an external flow, and proportional, inversely proportional to the viscosity. So it's just the ratio of those 2 forces. And so the idea of Reynolds number, and I guess I didn't show you one of the videos, so let's go back to that. It's relevant to what we're talking about here. I guess it was the first one. Yeah, so this is it. So this is flow within a pipe, a see-through pipe. You can see a little tube that's putting dye into it, which is scooting across from left to right. Yeah, left to right for you as well. And as it's looking at the effect of going downstream, and what you see is that it starts off, I don't know if the velocity is being changed, but if you change the velocity of flow in this pipe, instead of being laminar flow, which you can think of being a pack of cards which are skimmed across each other, the flow will become with vortices. It'll get turbulent. And so this typically scales with velocity. As you start with a very slow velocity, it will be laminar. Every particle travels exactly parallel to each other. And as you speed up the velocity within the pipe, you get these little vortices developing, and you'll end up being, the manifestation of that in this case is being able to look at these squiggles in the dye tracer in the center. And so presumably you're looking not only downstream, but also they're changing the velocity in this pipe to be able to get that. And it's getting a little more extreme as you go on. And so that you can index with the Reynolds number. And the Reynolds number is defined based on the characteristics of the system, the viscosity of the flowing fluid, the density of the flowing fluid, the velocity which is traveling, v, but also some characteristic dimension. That characteristic dimension could be the length from the injection of the dye, but that doesn't seem to make much sense. but the diameter of the tube is another dimension that's intrinsic to this system, which would seem to make more sense. And so going back to our discussion on these equations, is that if you look at, say, flow around a sphere, an external flow, if you have a Reynolds number that's less than about 1,000, what you tend to get is that all the flow lines around that sphere are such that they basically parallel each other, as you could imagine if you drew a kind of flow. You could imagine this being the case. And so as you go physically away from the sphere, the velocity on the sphere is zero because it's attached to it, and so zero velocity. But as you go progressively to the very far field, then the flow line here is not slowed down at all by the fact that you have a sphere here, right? It doesn't even feel it. And so if you drew a profile of the velocity away from this, then it would look something like this gradual change in velocity to the background velocity at some distance away from it. This would be the velocity. So that would be the case at very low Reynolds numbers, less than 1,000. It turns out to be low Reynolds numbers. If you pick up the velocity and make it go faster, then the profile of the streamlines as you go past here, instead of being, they might be close to this, but they might have a turbulent wake at the end of it. And so now if you draw the velocity profile as you go away from this, certainly it will be zero still at the sphere boundary, but as you go only a very small distance away from it, it will jump up almost to its original far field velocity. And so this fact that it makes this boundary layer, which is conditioned by the Reynolds number, means that we have to be able to account for the changes in the flow regime that occur with that. It would make sense that if you're looking at defining what the force is that you have to apply to this sphere to keep it static in a wind tunnel, it might change. It doesn't necessarily change as the flow domain flows around it, but it might do. So this would be a useful index to be able to apply. So kinematic similitude means that the flow, if you take a snapshot of the model, the flow regime changes from being a low Reynolds number flow to being a high Reynolds number. Laminar flow, pack of cards, versus turbulent flow when you get this very sharp transition in velocity from zero velocity here all the way up to the far field velocity within a very short. So this is the classic, I don't know if people are doing it in this class for their project, the classic idea that why a golf ball is dimpled is that a dimpled golf ball makes the surface rough. You'd think it'd be slower going through the air and it would take more force to push it through the air. But what the dimples on a golf ball do is they make it turbulent much earlier at much lower velocities, and at those low velocities this is much more efficient in pushing it through the air because you have this slip region which is really quite thin, and so you're not dragging against the viscosity. So it turns out that the controls on flow at relatively low velocities are viscous dominated. The controls on flow at high velocities are pressure dominated. The pressure that you apply here at stagnation versus the low pressure at the back. And so you'd expect in each of these regimes the forces that you apply in the systems to be slightly different. Okay, so geometric similitude has to look the same. Kinematic similitude, the flow field around it has to look the same. And then if both of these conditions are met, then you can establish dynamic similitude. And so dynamic similitude means that the Euler number of the prototype, well, let's do it the other way. We had a model. Euler number for the model is equal to the Euler number for the prototype. Just the same as for this. And so the Euler number, actually this is something we did derive on maybe the second time we met. You can do it directly from Bernoulli's equation by taking these two terms, as we did, and divide one by the other. You'd end up with an Euler number. When we were talking about dimensionality, since these are both units of length, if you divide a length, by definition it's non-dimensional. We can't derive a Reynolds number from this because we don't know exactly. We could do if we knew what this was in terms of viscosity. but there is no viscosity term in Bernoulli's equation. So Euler number is just the ratio of pressure forces to inertial forces. I guess it's so it's to inertia. The rho v squared is the same as half v squared over 2g term, right? Is really what this term is. And this is the pressure term, pressure force term. And really what you could also do is if you decide that pressure is equal to a force divided by an area, then replace, so pressure equals force over area. So if you replace this with that, then you have this. And so this is useful because if you know that in your model you're flowing exactly at the right regime, so you're flowing at the scaled regime, you could measure the force that's applied on your model, and then you could use that to calculate what the force would be on the prototype, basically, is what's going on. And so the idea is that similitude is just a mechanism by which you can look for similarities between a model and a prototype, between the geometry, the flow fields, and the forces that are applied to the model. And therefore, if you do the experiment on a model in a wind tunnel, you can scale up those forces that you measure in the wind tunnel to be able to figure out what they would be on the plane, to see if the plane will get off the ground at a particular speed, etc. So that's the gist of what dimensional analysis is. And so the reason for talking about it now, even though it was discussed in the material for last week, is that we could also apply that to pipe flow. We could also apply it to flow on a wing, external flows, and we can also apply it to open channel flows. And so the essence of what we'll talk about in the final portion of the class are that in weeks 10 and 11, these 2 weeks we'll talk about pipe flow. We'll talk about external flows in week 12, and after Thanksgiving, it's half-filled pipes, open channel flows. And the similarity between these is that for a pipe, we can define exactly how many variables that we'd have to accommodate to be able to get the relationships for flow in a pipe. We could do, if we wanted to, and we talked about it I guess it's in here, isn't it? We did talk about it. I guess I could go back to this. I don't mean to give you whiplash from all this, but is it this? We finished talking. No. Yeah, okay. The last stuff we talked about in terms of pipe flow. And so we said that in week 8 we talked about some equations called the Navier-Stokes equations. So we've got Bernoulli equation and we've got conservation of mass. We can take those and we can put them in Reynolds transport theorem, and we get conservation of mass and we get conservation of momentum written for any geometry we want. We can choose the geometry for that as kind of a differential geometry. And if we use those kind of complicated expressions that we get, which we didn't spend much time talking about, but they were these, the so-called Navier-Stokes equations. 3 equations for conservation of momentum in each of the 3 directions along with viscous effects, and 1 equation for conservation of mass. Variables of velocities at 3 directions in an element and a pressure, so 4 terms and 4 equations. If we solve those equations for simple geometries, we can come up with, for instance, an equation that gives us the volumetric flow rate in a pipe, and that volumetric flow rate is equal to 2 times the diameter to the power of 4, the viscosity, the pressure drop between upstream and downstream, and over the length of the pipe. So this would be L, and so we can get an expression that gives us directly what the volumetric flow rate is. But this is the volumetric flow rate only for what we'll call laminar flow, at flow velocities less than 2,000. So we could define for this, we talked about a Reynolds number, we can define a Reynolds number as a density times a velocity times a diameter and divided by a viscosity. So if we know what the diameter of the pipe is, and we know what the velocity of the fluid along that pipe, the average velocity, because we know it's parabolic, but if we take just the average velocity along the pipe, then we can come up with a volumetric flow rate through that. But it's only true for if the flow regime is appropriate. And so this equation here is only good if the Reynolds number is less than about 2,000. And so laminar flow occurs at a Reynolds number less than this, and if it's larger than this, it will be turbulent. And actually the equivalent of turbulent flow for this particular geometry, even though we don't need to look at it now, would be that the flow profile would look a bit like this. So these would be the velocities. So instead of being zero velocity here, it will be zero velocity here, but be a very sharp transition. I can't draw it well enough. It would be like this. So this would be the flow velocity for a Reynolds number greater than 2,000, and this would be a Reynolds number less than 2,000. And so this equation here applies only for these. And so we have no idea yet what this is. In fact, it would be very difficult for us to get this equation from these complicated expressions that we have. And so we have to use experimentation to be able to do that. And so that's what we'll talk about in this class. Okay. If I can find myself back to where we were before. I guess we're on a different sheet, weren't we? So if we come back to this, we'll find that the linkage between what we had talked about last week in terms of dimensionality or dimensional analysis is that we can do some experiments on a pipe and we can figure out exactly what the main variables are that control it. And so if you can think about what those variables would be, we could think that the pressure drop could be important. We could think that the velocity of flow could be important. We could think that the diameter would be important. We could imagine that the length would be important. What else? We could think that the roughness would be important. In other words, the undulations on this surface, for what we said about the golf ball and what dimples mean. We could imagine that both the density and the viscosity could be important. And probably, that might be it. 1, 2, 3, 4, 5, 6, 7. And so if you looked at this stuff already, you can know that the number of dimensionless variables that would control a system would be equal to the number of variables minus the number of units that describe it. And the units that describe it are mass, length, and time. So kilograms, meters per second. So within this group of parameters, pressure, density has units of mass per volume. So we definitely have mass and length represented. And velocity is units of length and time. So we definitely have time represented. So we have 1, 2, 3, 4, 5, 6, 7 of these units. So we have 7 minus 3, that's equal to 4. And we'll find out that the units that control the behavior would be the Euler number. It would be the Reynolds number would be the second one. So we need two others. So the easiest two others would be, it would also be given by the length over diameter. So these are linked to each other. And the other one is going to be the relative roughness. Epsilon over d. So to cut a long story short, we'll find out that the head drop along a system, head loss, is equal to a non-dimensional term, a friction factor, multiplied by length over diameter times v squared over 2g. If we go back to the top, I'll come back to it, but this is exactly what we wrote here. And so the essence of what we'll do with pipe flow is to be able to figure out exactly what this friction factor is. So the one question that we might have is, what is this friction factor? Well, the friction factor is a function of these two properties, the Euler number and the Reynolds number. It's not equal to them, but it's a function of them. And so what it requires is that we have some geometry in our system, which we can define in terms of this. We have a flow velocity, which we're moving at, and the magnitude of this drag force, which is really the drag that's placed on the fluid going through the pipe, is going to be it's going to be indexed by the Reynolds number. The Reynolds number requires that the flow regime is identical or is defined in a particular way. And then the Euler number is how the magnitude of the drag that occurs as a function of that. And so we won't do it today, but we will see if I can't make it. I guess I can make it. Don't know why it's not getting bigger. Doesn't matter. So the deal is that if we wanted to figure out exactly how a pipe worked, what we would do is we would have a pipe in the lab, and we'd have a pressure upstream and a pressure downstream, which we could measure. That would be our experimental variables. We'd use non-dimensional analysis to figure out exactly what the controlling variables would be in a rational way to do the minimum number of experiments. And then we would use that to be able to characterize the flow. And we'd find that the flow is a function of the Reynolds number and the Euler number. And we could place it on a chart, which I can make it bigger, which would look like this. So if we plot, for instance, the density and the velocity and the diameter of the pipe relative to viscosity, which is Reynolds number on this axis, and if we plotted the Euler number, which is the pressure drop along the pipe relative to the density of the fluid flowing and the velocity squared, and we did a whole bunch of experiments with a pipe at, say, using different velocities. And of course you see that velocity turns up here and it turns up here as well, so it's kind of interesting layout. If we did a flow test at some small pressure and we changed the magnitude of the pressure and we measured the developing flow rate that occurred and we plotted it, we found out that our terms would go on one line. We'd find if we kept on going at higher velocities, then we'd end up transiting onto a different curve. And so this is saying that as a function of these non-dimensional properties, and we're saying that these are the only properties that control our flow, Euler number, Reynolds number, and they define the magnitude of this friction factor, we'd have immediately defined the fact that we have a behavior which we've solved no equations to get, but we've just by doing experiments, we've been able to take these individual numbers. And so what we'll find is that we end up with a graph that defines behavior. There's a different behavior if we're looking at, this isn't written very well, as laminar versus turbulent. If I rewrite that. On this side, and turbulent on this side. And so immediately this defines a flow regime which at one case looks like the differences between laminar flow where everything's parallel to each other and turbulent flow where it's got vortices. And the essence of that is represented in this figure here. And we'll find out that the individual behaviors are such that if the flow is laminar, it will follow this single line for a given pipe circular section pipe. I guess it'd be a different one for a square section pipe, but only slightly different. And as you increase, and it's independent of the roughness of the pipe. But as you get turbulent flow, all of a sudden, just like the dimples on a golf ball setting off the turbulent behavior, then the friction factor for turbulent flow is a function of increasing roughness. So this would be for a small roughness, so I guess it would be a little roughness, and this would be for big roughness at the bottom. So as you go down, you end up on a different set of curves. And the reason for doing this is that these are defined in terms of these two numbers, an Euler number on the vertical axis and a Reynolds number on the lower axis. And the reason for presenting that here at this time is that what we'll do for the next few weeks has a certain similarity. So if you look at external flows, you think about an external flow being the flow around a wing that takes an aircraft off the ground. Well, an external flow is really just like an internal flow, but obviously the flow is on the outside. And so if you think about a pipe with a sealed end, then you're interested in the flow around that. You're interested in the flow regime being controlled by the Reynolds number, just as we said before. And the force that's being applied to that, instead of a force which is dragging against the flow and slowing the flow down here, which is what we're interested in pipe flow, in external flows, we're interested not in the effect of flowing down the flow, we're interested in the force that's applied on the structure. So it could be a lift or lift force on an airfoil, it could be a drag force on a car, or your head as you're cycling on your bicycle. But we're interested in being able to link these two together. And the link by which they're connected is that kinematically, we want the flow to be of a particular kind, to be indexed either laminar or turbulent. And if we know what that flow is, we can usually index that relative to an Euler number, which says, in this case, what is the stagnation pressure that's on the tip of this thing? And really the difference between the pressure on this side and the pressure on the back side is the force that's applied to keep it static in place. And so we're interested in the force that's applied on the structure here, we're interested in the force that's applied on the fluid here, but really they're the same thing. And so given the same geometry, it's not surprising that if you look at the figures that we'll use to define the behavior for external flows, it's really very similar to what we do for internal flows. We end up with a graph that defines an Euler number relative to a Reynolds number. This Euler number we call a coefficient of drag, and the coefficient of drag, I'm not sure I can remember what it is. Well, it's a force. It would be a force divided by a density, v squared, and it'd be and a diameter, an area, diameter squared. So this is a non-dimensional number, a pressure. So this force over area, kind of, right? This is pressure times rho v squared. So it's exactly the same as an Euler number. And this coefficient of drag, if it's a big number, then it's a big force that's being applied. And if it's a small number, it's a small force. And so this coefficient of drag is something that you determine. And in all the calculations we'll do, we're interested in looking at balances of forces. So you want to know how fast you'll free fall through the atmosphere. You can do that just by balancing forces. You fall through the atmosphere, there's a drag that's placed on your body along if you're going head first, it'll be on the top of your head and it'll be along the side of your body. So that's the force acting upwards. And the force acting downwards is going to be gravity. And so if you know the force that's acting upwards here, you can use it to solve for the velocity that you're traveling at. Simple as that. So that's all we do. So that's what we're doing for internal and external flows. And open channel flows are exactly the same. An open channel flow means that the pipe is only half full. It's a pipe flow, but the pipe is only half full. If it's only half full, then if you applied a pressure on the upstream, you'd get that pressure transmitted through the air directly downstream. So the only force driving this flow is not pressure upstream, but it's the weight of the water and the gradient of the pipe. And so we'll find out in this particular case, again, it's the Reynolds number that indexes the kind of flow it is. And now the Euler number that we bring out of it is something we'll call a Manning coefficient, which is like a drag. And for all flows that we have, they're almost all turbulent, so we only worry about them to the right of this diagram. But it's useful to kind of take stock of exactly where we are at this stage and see exactly where we're going, because these are the basic relationships that we'll use, and they're common between internal flows, external flows, and also gravity-driven flows. And the variables that control them are easily defined. And so as you look through the stuff for week 9, you'll see some examples, maybe using pipe flow to be able to characterize by dimensional analysis. So it's a very powerful technique that you can use, not just in fluid mechanics, in any kind of experimental setup that you attempt to do. And I'm probably going to leave it at that for now. Okay, so that's it. So we'll carry on with this next time. I'm trying to think what exactly we'll do. So if you look through, the notes are here. Actually, you'll see some diagrams which make sense. You'll see exactly this. You'll see this dimensional analysis, which you can use to be able to figure out exactly what the variables are. And then we'll start using it to be able to solve some problems. And this is exactly the chart that we'll use to do that. So laminar flow here, turbulent flow to the right of that. These lines are all horizontal, and there's some transition between those flows. So it's really, as I say, so it kind of links into maybe what I said about the exam. The tests now become a bit more formulaic. Calculate this, and so there's less perhaps interpretation of what the question is, and much more standard and formula.